All right, let's do this. We are going to take our understanding of sound and really lock it in by looking at its fundamental building blocks. We're going to see how you can construct any sound you can possibly imagine, right from the ground up.
This quote really sets the stage perfectly. It's getting at something deep. Sound is kind of tricky, maybe even more so than sight, because you can't see it. It's this invisible, abstract thing. So to really get a handle on it, we have to master the core ideas we're about to walk through. So where do we even begin? Let's start with the absolute bedrock, the physical reality of what sound is before it ever even gets to our ears.
Okay, here's the most crucial point to get. Sound isn't an object. It's not a thing. It's a wave of energy. When a speaker cone pushes forward or you clap your hands, you're creating these tiny, incredibly fast changes in air pressure. And that is sound. In this visual, it's the perfect way to picture it. It's just like a pulse traveling down a line of springs. See those spots where the springs are all squeezed together? That's called condensation. And where they're stretched apart? That's rarefaction. The key is, the energy is what's moving down the line, not the actual balls. They're just wiggling back and forth. All right, let's move on to our very first and simplest building block. Think of this as the atom of the sound world. You can't build anything complex until you understand the simplest possible unit. Imagine the most basic, clean beep you can think of, like from an old piece of electronics or a tuning fork. That's a pure tone. It's a perfect, simple, smooth oscillation. It's the simplest sound that can possibly exist.
Now, what's so cool here is that these three properties are really just different ways of looking at the exact same thing. Frequency, which we measure in hertz, tells you how fast the wave is wiggling. The period is just the flip side of that. How long does one single wiggle take? And the wavelength, that's the physical distance in space that one of those wiggles covers. They are all completely locked together.
Okay, so we have our little atom of sound. Now we need a way to measure it. How loud is it? How much energy is it actually carrying?
We have this progression because, well, the range of sounds we can hear is just astronomical. It goes from a whisper that's barely anything all the way up to a jet engine that can cause pain. If you try to use raw pressure or intensity, the numbers just get ridiculously huge and unwieldy. The decibel scale is what tames this beast, compressing that enormous range into a nice, manageable scale, usually from 0 to about 120. And if you remember one thing about decibels, let it be this. It turns multiplication into simple addition. So an increase of just 10 dB doesn't mean it got a little louder. It means the sound intensity multiplied by 10. A 20 dB increase? That's 100 times more intense. And 30 dB is 1,000 times more intense. It's a game changer for handling these numbers.
Okay, deep breath. Because this next idea, this is the most important concept we're going to talk about. This is the master blueprint for any sound in the entire universe. This is how we get from our simple atoms to literally everything else.
I mean, seriously, think about it. It seems impossible, right? How could you have one single framework that describes the beautiful structure of a violin note and the total chaos of a waterfall? The answer to that question completely revolutionized how we think about sound.
And there it is. This is the incredible, almost magical answer. Any sound you have ever heard, from your own voice to a car crash, is just a combination of those simple little atoms, those pure tones we just talked about. This is a powerful idea called Fourier's theorem, and it means we have a universal recipe for sound.
This image just lays it out perfectly. On the left, you see a few simple, clean waves. You add them together, and you get that messy, complex wave at the bottom. The graph on the right, that's called the spectrum. Think of it as the recipe. It tells you exactly which pure tones are in the mix and how much of each you need to add.
So that's our blueprint, the spectrum. It's a complete breakdown of a sound's ingredients. Instead of looking at how pressure wiggles up and down over time, we're now looking at a list of all the pure tones that make it up, all neatly arranged from low frequency to high frequency. So now we have two totally different ways to look at sound. But here's the catch. There's a trade-off. It's like a seesaw. Think about a super short, sharp click. In the time domain, we know exactly when it happened, but it happens so fast, it's a blur of frequencies. Now think about a long, sustained organ note. In the frequency domain, we know its pitch with perfect precision, but its exact start and end time get a little fuzzy. You can't know both with perfect accuracy at the same time. All right, enough theory. Let's put this blueprint to work and actually build something. Our first construction project, the rich, amazing sounds of musical instruments. We're going from the recipe to the finished product.
So unlike a pure tone, these sounds have real character and richness. Think of a piano, a guitar, someone singing a vowel. The waveform isn't a simple sine wave anymore, but it has a pattern that repeats itself perfectly. And it's that repetition that our brain hears as a clear musical pitch.
Now, when we look at the spectrum of a musical note, its blueprint, something incredible happens. It isn't random. It's not a mess. It is a beautiful, perfectly orderly series of spikes. This isn't chaos. This is pure structure. And each one of those lines is a specific pure tone in our recipe.
And these spikes are called harmonics. They follow a dead simple mathematical rule. Their frequencies are always whole number multiples of the very lowest frequency, which we call the fundamental. So if the main pitch is 100 Hz, the harmonics will pop up at exactly 200, 300, 400 Hz, and on, like clockwork. That rigid mathematical relationship is what our brains interpret as being music. Okay, so we've used our blueprint to build order. Now let's use it to construct two final things: the chaos of noise and the dynamic movement of modulated sound. And this comparison just says it all, doesn't it? On the left, you've got that beautiful, orderly series of spikes for the musical tone, and on the right, that's noise. It's just everything. All the frequencies are jumbled together into this continuous, chaotic mess. The recipe for a tone is precise. The recipe for noise is dump everything into the bowl at once.
So let's nail these last two ideas down. Noise is all about one thing: randomness. That's it. Modulation, on the other hand, is a fancy word for adding change over time to a sound. Amplitude modulation is just like turning a volume knob up and down really fast. And frequency modulation? That's like twisting the pitch knob back and forth, which gives you the sound of a siren or a singer's vibrato.
And there we have it. We started with a simple pressure wave, we found our atomic building block, the pure tone, and we discovered the master blueprint, the spectrum, that lets us build harmonics, noise, and everything in between. We have the recipe, the ingredients, and the instructions for literally anything we can hear. So the question is no longer, what is sound? The real question is, now that we have the blueprint, what can we build?